Welcome back. We've done a lot of work so far in terms of giving the basic definitions and exploring their properties. We've looked at definitions of not just convexity, but smoothness, strong convexity, and then we explored what that basically means. And we saw that for smooth functions, a function is beta smooth exactly if it has a quadratic upper bound that approximates it. A function is strongly convex if it has a quadratic lower bound. And a function is, if it's just convex without either necessarily smoothness or strong convexity, then all we have is the basic property of convexity that a function can be, is lower bounded by its linear approximation. We're going to look at all three of those and finally, after all the work we've done, see how they translate into specific rates of convergence. In other words, guarantees for first the subgradient method and then for gradient descent. So the first thing that we're going to do is look at the subgradient method. And again, this algorithm is the setting where my update, x plus, is going to be x minus a step size, and again, not a gradient because I'm going to apply this to functions that may not even be differentiable. So we'll need to replace the gradient with an element of the subdifferential. And then we're going to look at gradient descent for smooth functions and for smooth and strongly convex functions. In this case, x plus is going to be x minus my step size times the gradient of f of x. And our goal in all of this is to obtain bounds on the suboptimality. Meaning, I want to look at f of xt minus f of x star, where x star solves the problem minimize f of x, subject to x in all of Rn. So we're still looking at unconstrained problems. As soon as we establish these convergence results and the basic analysis techniques for these algorithms, we'll see that this is quickly going to translate into what we need for constrained algorithms. So this is important groundwork that we're laying right here. So what I want is to obtain upper bounds on this in terms of parameters of the problem. But most importantly, I want to know what is the dependence of this gap. Note that this is always going to be greater than or equal to 0 because f of x star is the minimizer for any value xt. F of xt is going to be greater than or equal to f of x star, so this is not negative. So I want to know is what does this gap look like as a function of t, the number of steps that I've taken. So let's get to it, starting first with the most general class of functions that we're going to consider, which is functions that are convex and also, again, have this property that we've talked about, that they don't have infinite steepness. Another way we can say it is that basically they're going to be Lipschitz functions. So let's let f be a convex function, for now defined on all of Rn. Not necessarily smooth, not necessarily strongly convex, but I will assume that it has this bounded steepness condition. And another way to think of that is if I could compute a gradient, bounded steepness would basically be saying that the gradient is bounded. The norm of the gradient is bounded. It never gets arbitrarily steep. But in our case, we don't necessarily have a gradient anywhere. We have subdifferential. So we're going to assume that for any value of x that we look at, for any subgradient in the subdifferential of f at that point, there's a uniform upper bound. And in particular, the bounds, the results that we're going to get are going to depend on what this g is. So let's see what we can say. So what do we know? We're going to use the subgradient method. For now, we're going to leave the step size as arbitrary or undefined, and then we're going to see later what value we should choose. The subgradient method again says xt plus 1 is equal to xt minus this as of yet undefined step size times gt, where again gt is some element of the subdifferential of f at xt. Now remember that this that the subgradient method is not necessarily a descent method. So we've seen this before. That means that f of xt plus 1 might actually be strictly greater than f of xt. So we can't hope to leverage some aspect of that descent. But nevertheless, we know that this will give us the optimal solution. So let's see how that works and try to appreciate some of the subtleties of this. We're going to start by looking at this gap. Now, as a general comment and something to keep in mind as we look at all of these proofs, you may wonder to yourself as you're watching them unfold, why did we set it up in one way or another, or how would I have come up with this idea? And the good news here is that there's really only a couple different ways that all of these proofs go. And initially, if you haven't been exposed to them before, it may seem that it's kind of coming out of nowhere, the steps are coming out of nowhere. But really, there's going to be just one of, the way that this proof proceeds is going to be one of a few different possibilities. And if you look again, as this course progresses, you look at all of the different proofs for convergence, they're all more or less start the same way. And the other thing that you should be thinking of as you see any particular proof of convergence is, what are our assumptions and where do they come in? How are they going to be used? So here we don't make too many assumptions other than convexity. So you should expect that we're going to use in a fundamental way this property, keep defining property of convexity, namely that a convex function is lower bounded by this linear approximation that uses the subgradient. Then when we talk about smoothness, you should be waiting to see, where does smoothness come in? And it's going to come in one of a variety of different ways potentially. We've spent some time proving properties of smooth functions. And similarly for strong convexity. So this is a right way to anticipate and to look at any proof that you see. The reason I mention this is that there's no big mathematical hammers that we're using here from step to step. It's just pretty simple algebra. So it's easy to get lulled into, yeah, just, step A follows from step B, C, D, etc., and not really appreciating what we're doing other than just some simple algebraic manipulations. And honestly, that's really the only reason that it's actually worth looking at the proofs, to appreciate the result a little bit more and understand where the assumptions come in, how they're used, how they get us the results. Otherwise, it's just simple manipulations from step to step, basically no more complicated than manipulating quadratics. So let's have a go at it and see and try to keep all of these things in mind. So xt plus 1 minus x star, I see an xt plus 1. Here's my opportunity to plug in my recursion. So this is equal to xt minus eta times gt, that's my xt plus 1, minus x star. Okay, well, now I'm going to expand this quadratic, and I'm going to group xt with x star. So this is xt minus x star squared. I've also got the square of this middle term here. That's eta squared times gt squared. And then when I expand a quadratic, I have the first term squared, the second term squared, and then I need to subtract twice the cross term. So the cross term in this case is minus 2 eta times gt xt minus x star. This is what we've got. Okay, second step here. We're thinking about convex functions. If it's not already, it should become ingrained. Whenever you see something like this, whenever you see something like gradient or subgradient, times the difference of 2 points, that's the key thing that we need in order to bound the difference of two functions, the difference of a function evaluated at 2 different points. And remember that, so whenever you see this, you should immediately be thinking, we should be thinking about the key definition of convexity, namely f of y is greater than or equal to f of x plus the gradient or subgradient times y minus x. And that's what this term looks like. Right? This is what it looks like. So it's going to give me a lower bound or an upper bound, depending on which side I put it. You know, if it's on the, is it on the right or is it on the left, of the difference between f of x and f of y. Okay, so let's see how. Back to my main color. Let's see what this gives us. So this is less than or equal to. First term stays the same, xt minus x star squared minus 2 eta, and again, exactly as we should expect from this, the difference of f evaluated at 2 different points. What 2 points? Xt and x star. F of xt minus f of x star. Again, I would encourage you, I'm skipping the exact step of doing all the details, to encourage you to just write this inequality out and see which side did I put it on. You know, how exactly did we go from this step to the last step that we've got. And then I still need to add my last term in here, eta squared times gt squared. But instead of writing it like this, let me just go ahead and use this uniform bound. So let me simplify this by writing eta squared times g squared up there. Okay, now we see we've gotten this far. What comes next here? So I'm going to highlight 2 different terms. So you see that I've got an xt plus 1 minus x star, less than or equal to xt minus x star. This is another very, very common element, very common ingredient of basically all proofs that you'll see whenever you're trying to control an iteration. We're going from x1 to x2 to x3 to x4. We're going to apply it again and again and again. And if I repeated this iteration, this is basically a recurrence relationship. I've bounded xt plus 1 minus x star, that's my first term, with xt minus x star plus some other stuff. So I could presumably just repeat this, and xt minus x star would be bounded by xt minus 1 minus x star plus some other stuff. So I could repeat this over and over again. And whenever we see this 2 terms that look like this, it should make us think about the possibility of forming a telescoping sum. So let's do that. Let's do that by rearranging this inequality and seeing what we've got. So I'm going to move this term over to the left, and I'm going to move this term over to the right of the inequality. And this is going to give me, once I divide by 2 eta, it's going to give me that f of xt minus f of x star is less than or equal to, here's my 1 over 2 eta that I divided by. And then what was left on this right-hand side? I had this first term, xt minus x star. So let's put that there, xt minus x star. I have the term that I subtracted, that I brought over from the left-hand side with a negative sign, xt plus 1 minus x star squared. And then I had the third term on the right-hand side from before, my eta squared g squared. And eta squared divided by 2 eta is going to give me eta over 2 times g squared. Okay, so now this is going to form a telescoping sum. In other words, this will telescope once we sum over t. Again, very common ingredient. You're going to see this in many of the results that we're going to derive in this course. So I'm going to sum both sides over t from little t equals 1 to capital T. That's the number of iterations of gradient descent of subgradient method that I'm going to run. And I'm going to divide by t. So 1 over t times the sum of f of xt minus f of x star. What did I do? Divided by t, sum from little t equals 1 to t is less than or equal to. I need to do the same thing here. This is where the telescoping is going to help me. What happens when you telescope? What's left? The first term minus the last term. So this is not going to be a sum, but rather I'll have 1 over 2 eta times 1 over t. And what's left is the first term minus the last term. In other words, x1 minus x star squared minus xt minus x star squared plus 1 over t times the sum of eta over 2g squared. But note that there's no t over here. So I'm just summing the same thing. So that means that the sum and the 1 over t cancel. So in other words, I can just simplify this whole term to be just eta over 2g squared. So let me just replace it with that. I'm going to erase this. And I've got my my eta over t g squared. Okay, so how can we simplify this a little bit further? This is an inequality saying that the left-hand side is less than or equal to the right-hand side. So that means that I can certainly, it's only helping my life that I've got this, that I'm subtracting this. So I can cross this out. I can drop this without affecting the inequality. So I'm not saying that it's 0, but I'm just pointing out that dropping this term respects the inequality. I was subtracting something. I'm no longer subtracting it. That thing was positive. I could only make the right-hand side bigger. So this less than or equal to still holds. Okay, that's a little bit simpler. Now let's have a look at this left-hand side here because it doesn't seem to be exactly what we want. Now I claim that this left-hand side, there's something that's smaller than this left-hand side, something that's lower bounded, that lower bounds this left-hand side is the sum of f of, oops, not the sum, f of the average. Minus f of x star. So let's think for a second, why is this true? I had the average of f of x, and I'm saying that the average of f of x is greater than or equal to f of the average. So if you think about that for a second, that is exactly the fundamental definition of convexity, the very first definition that we gave, which basically says that if I have a convex function, then the function evaluated at the average of points always lies below the function, the average of the function. Not just the average, any convex combination, but in particular for the average. In other words, take 2 points, the chord that joins them always sits above the convex function. That's exactly what this inequality is saying. So f of the average is minus f of x star. The suboptimality of the point that you get from averaging the trajectory is less than or equal to the average suboptimality, which is less than or equal to the right-hand side. So this is less than or equal to 1 over 2 eta times t times, what is this x1 minus x star? This is another thing that we need to give a name to because x1 is some arbitrary initialization point. And I don't want to make any assumptions about knowing how to initialize. So this is some value that I basically have to live with. So I'm going to call this r squared. So we've talked about this before. x1 minus x star, I'm going to call this value r. This is essentially, actually let's even write just less than or equal to. So this is just saying that I initialize somewhere and I just know that it's not infinitely far away from my solution. I have some upper bound. So on the right hand side I have 1 over 2 eta t times this value r squared plus eta over 2 times g squared. So what do we want to do here? On the one hand, eta needs to be small, because if eta is small, then it's going to make the second term, eta over 2 times g squared, small. On the other hand, if eta is too small, then this left-hand side, I've got an eta in the denominator. So if eta is too small, then it's going to make that first term big. So I need to balance these. And you can see that the balance, the optimal eta, the best eta, behaves like 1 divided by square root of t. So how can you actually verify that for yourselves? Well, first of all, just intuitively, looking at these expressions, I've got a 1 over eta t and some other constants. And then I've got an eta in the numerator. So if eta is 1 over square root of t, the first term, 1 over eta t, looks like 1 over root t. And the second term, which has an eta, again looks like 1 over square root of t. So again, I've balanced these. If eta is any bigger, then the second term, eta over 2 times g squared, is going to scale faster as a function of t. If eta is any smaller, then the first term, 1 over 2 eta t, is going to scale faster as a function of t. So this is the balance. But if you want a more precise argument, you could just notice that this right-hand side is a convex function of eta. So you could just take the derivative, set it equal to 0, and find the best eta. And so you'll find that the best eta is going to be 1 over square root of t, and then it's going to combine these other constants that you see in there, r squared and g squared, in some way. So that's a good exercise for you to try to do, optimize this right-hand side. So let's consolidate some of what we've learned here. So our summary of subgradient descent, of the subgradient method, is as follows. First, if we plan to run for t iterations, then the best step size to choose scales like 1 over square root of t. So this is interesting. If you think back to our example of that polynomial function for which we used gradient descent, eta was just some fixed value. When I say fixed value, I mean one that didn't depend on the desired error, didn't depend on the number of steps or anything like that. But here we have something different. So eta has to be 1 over square root of t. Secondly, the error after t iterations scales like 1 divided by square root of t. So shall we look at that expression again? Our error here is 1 over eta t I'm ignoring the constants here for this discussion. 1 over eta t. Eta is 1 over square root of t, so it's 1 over t divided by root t. That's 1 over root t. That's the first term. It scales like 1 over root t. And the second term is eta times some constants. So again, 1 over square root of t. So our error after t iterations scales like 1 over square root of t. Another way to write this is that to have error epsilon, how many iterations do we need as a function of epsilon? We need, if we think about it for a second, I'm equating 1 over square root of t with epsilon. That means I need 1 over epsilon squared. I need the order of 1 over epsilon squared iterations. So first of all, this should be good news for us, because what this tells us is that subgradient descent works. We had already said that subgradient, the subgradient method is not even a descent algorithm. But here we showed that if we run it for t steps and we average the iterations, in other words, if we run it for t steps, subgradient descent, the subgradient method gives us an algorithm for obtaining a point which is 1 over root t suboptimal. And that's going to 0. So this is basically telling us that the subgradient method is going to find the optimal solution. For starters, subgradient method produces an epsilon optimal solution. That's good news. Another very important point here is that if you look at the number of iterations that we need, there is one important thing that's missing, and that is there's no function of the dimension. In other words, if I double the dimensions of my problem, or quadruple, or multiply by any amount the dimensions of the problem I'm solving, the number of iterations I need in order to get epsilon error is still going to scale like 1 over square root of t, like 1 over square root of t. I don't have anything that depends on the dimension in terms of how many iterations I need. And this is one of the reasons that gradient descent and the subgradient method are sometimes called dimension-free. We'll be talking about this more. But it's also a reason why they're extremely well suited to problems where we're not obsessed with epsilon being very small, but our problem might be very large size, very high dimensionality. And this is yet another reason why we see these kinds of methods being used a lot in machine learning. Because for many problems in machine learning, of course in some we really do require very high accuracy, but for others, having a modest epsilon, maybe 5% error, 1% error, but not something like 10 to the minus 16. So if you have that kind of error, 1 over epsilon squared is not quite as scary. On the other hand, if your problem is very big, then this is really a winning kind of situation that you want to be in. So this is good news. That said, let's try to get some more good news for ourselves by continuing on to more structured classes of functions. So this is somehow our base result that tells us that as long as our function is convex, we're going to get subgradient method is going to work, and it's going to work with this rate. So we should expect to do better if we have smoothness or if we have strong convexity. And this is exactly what we're going to see. So let's assume, so we want to look at the problem, minimize f of x, again, no constraints, when f of x is a beta smooth convex function. What are we looking to see here? We're looking to see where we use properties of smoothness, in particular this quadratic upper bound. And at an intuitive level, what we should be thinking of is when we minimized that polynomial function, 3x squared plus 4x, whatever it was, what we saw was that the step size we took was just had to be something like 1 over 6 or less than 1 over 6. It didn't have to scale like 1 over square root of t. And the key thing that we used was this property that we've called the self-tuning property. As we get closer and closer to the optimal solution, the gradient vanishes. And what that allows us to do is we don't need to have a very, very small step size. We're not going to overshoot if we've properly tuned it. So let's look at the proof of convergence and keep our eyes open for where the key assumptions of smoothness come in and where we can use this self-tuning property. It's worth in this discussion to flip back to the proof of the subgradient method and see where did the absence of that self-tuning property come in to hurt us. And we'll do that as soon as we make a little progress here. Okay, so remember we've discussed that based on our quadratic upper bound, the algorithm that we're going to use is gradient descent with step size 1 over beta. So our update is going to be xt plus 1 equals xt minus eta set to 1 over beta times the gradient of f of xt. So in other words, I'm going to choose this value. And so let's see what we get. So also recall that as long as eta is less than twice this value, we're guaranteed that we have a descent algorithm. So recall that for eta this size, we have f of xt plus 1 is less than or equal to f of xt minus eta over 2 times the gradient of f of xt. This holds for any eta that's less than or equal to what we have here, to 1 over beta. Okay, what comes next here? This is equal to, less than or equal to f of x star, the optimal solution, plus the gradient of f of xt times xt minus x star minus eta over 2 times the gradient of f of xt squared. Where did this come from? Where did this inequality come from? Well, this is just like we discussed in the proof of subgradient method. You see this term here. So we've used just the basic inequality of convexity. And that's how we got from f of xt to f of x star. Again, think about how we used it. So we did not use a quadratic upper bound. So I didn't use f of xt is less than. I can't use that. I'm using the inequality that I use is f of y is greater than or equal to f of x plus the gradient times y minus x. So think for yourselves, what was y and what was x in that basic defining property of convexity in order for me to get this step. Okay, and this is in turn equal to f of x star plus 1 over 2 eta times xt minus x star squared minus xt minus x star minus eta times the gradient of f of xt squared. Again, what did I say about these general proofs? There's a few parts where there's insight. There's a few steps of the proof that are using key properties that we've derived, or key properties of the function, smoothness in this case, and convexity. And everything else is essentially like playing with quadratic. So this last step is just rearranging the term of a quadratic. You can just expand these two quadratics out and see that all the terms above are accounted for, and I haven't added anything else. Okay, what else do we recognize here? This is exactly xt plus 1 minus x star squared. And because xt minus eta times the gradient of f of xt, that's my xt plus 1. Again, we see our ingredient that we saw in the last time. This is going to be a telescoping sum. So bringing down f of xt plus 1, this is what we have so far. And this is going to telescope once we sum. So this is exactly what I'm going to do. I'm going to bring f of x star over to the left-hand side, and then sum both sides and divide by t. So I find that f of xt minus f of x star is less than or equal to 1 over t times the sum of f of xt minus f of x star. So think about where did this inequality come from? I'll leave that as an exercise for you to think about it. And this is less than or equal to the sum of these terms here on the right hand side that are left divided by t. But we're going to telescope. So I've got my 1 over t. I've got my 1 over 2 eta. And again, rather than seeing a sum here, I'm just left with the first term minus the last term. Because this is a less than or equal to inequality between the left and the right, I can just drop subtracting that last term, exactly like we did before. So I hope you're starting to see some of these things, some of the standard manipulations that we do. So this is just x0 minus x star squared. So and that's it. This is our story. Right? So we've got 1 over t times 1 over 2 eta. So with our choice of eta, this looks like beta over 2 times what we called before r squared. I really want to focus on the convergence of 1 over t. Note that I don't have to choose eta shrinking. Eta is not equal to 1 over root t. And that's really the win that I get. My eta was just some fixed value. So what do we see? We have our error, our suboptimality in other words. Let me write it that way. Suboptimality scales like 1 over t. That means that if you want suboptimality epsilon, how many steps do you need? You need about 1 over epsilon steps. So we should compare this to what we had before. After t steps, we had 1 over square root of t, error. And for error epsilon, we had 1 over epsilon squared. This is a lot faster. So just think about epsilon, you want, say, 99.9% accuracy. Then 1 over epsilon is 1,000 versus 1 over epsilon squared, which is 1,000,000. Before we move on to strongly convex, let's briefly flip back and see where things went differently with subgradient descent. So there's a lot going on here, but let's focus in on this line right here, because this looks very, very similar to what we just saw. The only difference is that this final term was not there in the previous one. And so when we looked at, when we got our final convergence, we were forced to basically add g squared error at every single step. What's g squared? G squared is the value of the gradient, the value of the subgradient. This is where our that g squared came from. And we were forced to accumulate this. And that's what contributed to this eta g squared in the final bound. And essentially, this is the reason that I had to balance the left and the right sides. And I had to take eta very, very small. If I took eta very big, then this term would be quite small if I took eta big. But on the other hand, that would make this term grow. So it was this balance that exactly accounts for this decrease in rate from 1 over t to 1 over square root of t. And where does this come from? It comes from this lack of self-tuning. So there's no self-tuning property. That is the key. So let me just note this again. Note the use of what we've called the self-tuning property. of smooth functions. We've got a little more to go here. We're going to talk about now gradient descent for smooth and strongly convex functions. And finally, we're going to use this property of CoCorrosivity, which we worked pretty hard to derive. So remember that what does this property tell us? It tells us that if f is beta smooth and convex, then the gradient of f of x minus the gradient of f of y dot product with x minus y, ordinarily this is just greater than or equal to 0. In our case, this is greater than or equal to 1 over beta times the gradient of f of x minus gradient of f of y squared. Okay, so we're going to use this. So we're now going to assume that f is both smooth and strongly convex. Assume f is alpha strongly convex and beta smooth. So remember that if f is alpha strongly convex, the definition here is that the function f of x minus alpha over 2 is convex, but also note that this function has some smoothness properties. Also, this is beta minus alpha smooth. Now remember, how would we show this? Remember that our property for smoothness tells us that, how would you show this? Remember that f is, let me write, instead of beta, maybe it's more clear if I write a generic constant, gamma smooth if gamma over 2 x squared minus f of x is convex. By assumption, f satisfies this with gamma equal to beta. And now look at this function f of x minus alpha over 2x squared. You can easily check that this satisfies smoothness with beta minus alpha. So then let's apply CoCorrosivity to this function. CoCorrosivity of f of x minus alpha over 2 x squared implies that once you plug it in, simplify everything, this is just algebraic manipulations, it tells us that the gradient of f of x minus the gradient of f of y times x minus y is greater than or equal to alpha times x minus y squared plus 1 minus beta minus alpha times gradient of f of x minus gradient of f of y squared plus alpha squared over beta minus alpha times x minus y squared. And now I need to do, oops, and I have one more term here, minus 2 alpha over beta minus alpha times the gradient of f of x minus gradient of f of y times x minus y. And now I notice that I have this term on the left. I also have this term on the right. If I bring this over to the left, collect terms, and divide through, then I find that, so simplifying, we find that CoCorrosivity implies that the gradient of f of x minus gradient of f of y times x minus y is lower bounded by alpha beta over alpha plus beta times x minus y squared plus 1 over alpha plus beta times the gradient of f of x minus gradient of f of y squared. So note that this is somehow a combination of coercivity, which is that the left-hand side is bounded by a function of x minus y squared, and CoCorrosivity, which is that the left-hand side is bounded by a function of the difference of the gradients. So this is, in order to obtain this, we had to use both strong convexity and smoothness in order to get this. And this will be a key element of our proof of convergence for gradient descent for smooth and strongly convex functions. So what do we have here? We're going to take step size eta equal to 2 over alpha plus beta. So a little bit different, a little bit bigger than the step size that we took before. And gradient descent update is going to be just like before. Xt plus 1 equals xt minus eta times the gradient of f of xt. And now let's see how the algorithm proceeds, how the bound proceeds. Xt plus 1 minus x star is equal to, just plugging in what the iteration is, this is equal to xt minus eta gradient of f of xt minus x star squared. Just like we did before, I'm going to expand this quadratic. This is equal to xt minus x star squared. So these terms should start looking a little familiar. Minus 2 eta, this is my cross term, gradient of f of xt times xt minus x star, plus the square of the second term, which is eta squared times the gradient of f of xt squared. Now I'm going to use CoCorrosivity, but where? Note that this is actually equal to, because I'm unconstrained, it's equal to the gradient of f of xt minus 0, but 0 is, another way to write 0 is the gradient of f of x star times xt minus x star. These two terms are equal. And now I'm in business, because this is exactly what I can lower bound using the expression that we had on the previous page. So let me write this. Let me write down what we had on the previous page. So this is greater than or equal to a term that had an x minus y squared and a term that had the difference of the gradients. So this is greater than or equal to alpha beta over alpha plus beta times the difference of the points, xt minus x star squared. This is good because that's going to merge with this, plus 1 over alpha plus beta times the difference of the gradients, gradient of f of xt minus gradient of f of x star squared. Remember, gradient of f of x star is just 0. So this term here is going to help me deal with this term. So using this, putting this inequality, let's see what direction the inequality goes in. I'm replacing this with something smaller. That means I'm subtracting something smaller, which means that if I'm subtracting something smaller, I'm potentially making things bigger. So I've got the coefficient of this, 1, minus the coefficient that I'm going to get here, 2 eta alpha beta over alpha plus beta, times xt minus x star squared. That takes care of this term and this term. And now I have my second term here. So this is equal to eta squared, that's this term, minus 2 eta, that comes from here, times 1 over alpha plus beta times, I'm going to stop writing gradient of f of x star. I'm going to go back to calling that 0 and not bothering to write it. This is bounded in this way. And now you can see why my choice of eta was so important. If eta is equal to 2 over alpha plus beta, you can see that this term on the right basically is greater than or equal to 0, is equal to 0. And so this side here is, I can just stick with the first term. 1 minus 2 eta times alpha beta over alpha plus beta times xt minus x star squared. And this is exactly what we wanted, because bringing this down, we see that what we have is a contraction at every iteration with some constant that's strictly less than 1. So as long as my eta is not too big step size, and I've taken care to make sure that it's not too big, this is a contractive factor. And that means that every time I iterate it, I can keep going, and I'll get that this is less than 1 minus 2 eta alpha beta over alpha plus beta raised to the t times x1 minus x star squared, which was equal to my r squared. This is very similar to the behavior that we saw when we looked at that function 3x squared plus 4x, that polynomial, and we saw what gradient descent is able to do. So this tells me, finally, if you simplify this a little bit, you'll see that we get xt plus 1 minus x star squared is less than or equal to, there's a reason for manipulating it in this way, beta over alpha minus 1 over beta over alpha plus 1 squared xt minus x star squared. We can just take the squares away from everywhere, and we see that this is my contractive factor. And so if I replace this with a 1, I can put a t up here. So what kind of convergence rate does this give me? Oh, well, why did I write it like this in the first place? Beta over alpha, sometimes denoted by kappa, is called the condition number. And it's just a more compact way of writing this. It's always less than 1. Note that beta is always greater than or equal to alpha. So this thing is always well defined. So my summary is that for f alpha strongly convex and beta smooth, we have suboptimality is controlled by something that looks like a constant times, let me not write minus here, this constant could be less than 1, a constant raised to the t. So it decays very, very quickly. What is that constant? It's exactly what we've derived here. So c is equal to kappa minus 1 over kappa plus 1, where kappa is equal to alpha over beta. Oops, beta over alpha. So this means that in t iterations, we get very small error. And for error epsilon, how many iterations do we need? We need about, for error epsilon, we need about log of 1 over epsilon iterations. So for subgradient, we have error that scales like 1 over square root of t. In other words, we need 1 over epsilon squared iterations. For smooth, we have error that scales like 1 over the number of iterations, which is equivalent to saying I need 1 over epsilon iterations to get epsilon error. And for strongly convex and smooth, I have the number of iterations I need is log 1 over epsilon. So I need something like c to the t. Remember, c is less than 1, is my error after t iterations. In other words, I need log 1 over epsilon. You can see how much faster each one of these is. We're going to stop here and pick it up next time.